So class, the subject of today's video is the real Newton's second law for rotation, similar to how we had a real Newton's second law for translation. And in the process of this video, we shall be introducing the important concept of angular momentum. So let's recap what we have about translational Newton's second law. In the beginning of the course, I introduced Newton's second law as the sum of all the forces is equal to mass times acceleration. Then we went through the course a little bit and talked about various applications of F equals ma using free body diagrams and all of that. And then I told you later when we came to the momentum chapter that this is not the true Newton's second law. Newton never wrote that. Newton in fact wrote something more general, and that is the sum of all the forces is equal to the rate of change of linear momentum. That's what Newton wrote. And the reason this is more general than that is because let's put what momentum is. Momentum is mass times velocity. And here I'm going to assume that the mass does not change with time. So I can, if I assume the mass does not change with time, I can take the mass outside and I get F equals ma, because it's going to be m dv by dt, which is F equals ma. But what if mass does change with time? For example, you have a rocket. Most of the rocket's mass is in fact lost by the time the rocket exits the atmosphere. So in that case, you will have to consider the mass of the rocket as changing with time. So it's going to be dm by dt times v, that's one term. And the second term is going to be m times dv by dt. Now, for example, a rocket, these are the external forces here acting on the object. In outer space, there is no external force, so that's going to be 0 for a rocket. But this tells you the rocket keeps speeding up. dv by dt, the acceleration of the rocket, is not 0 because it's provided by this term. The rate of change of mass for a rocket is negative because it's losing, its exhaust is getting burned out. So it's dm by dt is negative, so it goes to the other side of the 0 and causes the rocket to go faster and faster. And that's how a rocket is able to speed up even in outer space. So this is certainly a more general way of looking at Newton's second law for translation. So you might expect a similar story for rotation, and you will not be wrong. For rotation, we started out with the sum of all the torques. To be precise, I need to put external torques is equal to the analog for mass in rotation is the moment of inertia, and the analog for linear acceleration is angular acceleration. So sum of torques equals I alpha, and just like we did problems here, we did some problems here involving massive pulleys and compound pulleys, falling objects like meter sticks and non-uniform rods. You can do all kinds of problems with this, but this is not the most general Newton's second law. To find a generalization of this, we realized that torque is just R cross F. So maybe we can take the cross product with this thing. So let's do that. Let's take R cross F. Well, if I take R cross F, I'm going to get the sum of all the torques here. And here, if I take R cross P, that's what's going to be the new momentum. So I'm going to call this d by dt of the angular momentum L, where L is now equal to R cross P. Let's just try to make sense of this one. If this actually gives us something like what you expect. So if I put L here, R cross P, let me see what I get. I'm going to get d by dt R cross P, so I'm going to get dr by dt cross P, and then I'm going to differentiate the other term, which is P, so that's going to be R cross dp by dt. Well, dr by dt is just a velocity, so I'm going to get velocity cross mass times velocity. Well, the cross product of a vector with itself is going to be 0 because the angle between the vector and itself is 0. Remember, the cross product is equal to the magnitude of one vector times the magnitude of the other vector times the sine of the angle between the two. and in this case the angle between the two is 0. So I just get r cross, well, dp by dt, which is precisely f external. So I am getting what I expect. So this works out. As long as we define a quantity L equals r cross p, which is the replacement for Newton's law. So this has the same status as that does. So this is the new generalized Newton's second law for rotation, in the same way as this was the generalized Newton's second law for translation. So let's see how we can use this. Angular momentum L is r cross p, and by the way, this definition is valid for a point mass. Let's take a look at that definition a little bit. So if you have a point mass moving with some speed v, mass m, the linear momentum is going to be in the same direction as the velocity, so that's going to be p. And let's see how the angular momentum looks like from some point which I'll call the origin O. So the r vector is going to be this one. So r cross p, using the right hand rule, we see that the angular momentum has to be into the page. So I'll draw that here. It's into the page vector. That's the angular momentum. Now what about the magnitude? The magnitude of the angular momentum is going to be rp sine theta. Well, this can be written where theta is this angle here. So I'm going to write this in a little interesting way. If this angle is theta, then this can also be written as r sine theta times p. And r times sine theta is precisely the height of the object. So that's going to be, p is mv, so that's just mv times the height. So basically what I've tried to show you is that if you have a point particle moving at a constant speed, and if you're looking at that point particle from some distance, the angular momentum is going to be constant. It's just going to be the mass times the speed times the distance of the object, the direct distance of the object. So if you have an airplane flying at a constant height, its angular momentum is always going to be constant, and it's going to point in a direction given by the right hand rule. But what if you don't have a point mass? What if you have an object that's a rigid body? So a rigid body like a top, for example. I have here a top with me. So it's a solid object, and it's made up of all these mass points, but it's all rotating together. So how do we make sense of the angular momentum of something like this? So let's do that next. The angular momentum of a rigid body. So I have here a rigid body. And it's rotating about some axis with some angular speed, which I'll call omega. So each of the mass points within the rigid body is executing a little circle. Let's call the radius of that circle r sub I, and the mass point itself is m sub I. And the mass point has got a tangential speed, which I'll call v tangential sub I. So the angular momentum can be found by taking the formula for the angular momentum for a point mass and simply summing it up. So the angular momentum of the ith particle, just considering the magnitude, it's going to be, the direction is going to be r cross p. So that's r cross p. It's going to be in the same direction as the omega vector. So the angular momentum is rp sine theta, ri pi sine theta, and the angle between the ri and the pi vectors is simply 90 degrees, so that's just sine 90 degrees. And this is going to be ri mi vi. Now v equals r omega by the connection between translation and rotation, so that's going to be ri squared mi omega. Now I don't write omega I because omega is the same for all the mass particles. Now if I sum up all these things, then I get the total angular momentum. It's going to be the sum of all these li's, and I can pull out from that summation sign this omega, and I get sum of mi ri squared. Well, that's our old friend, the moment of inertia. So that's just I times omega. Now I can write this as a vector equation with no additional effort. And so for a rigid body, we have this equation for angular momentum. Now it's my custom when I introduce a new physics quantity to also look at the units. So let's do that next. The units of angular momentum. Let's first do it for the point mass. Well, that's meters, SI units of meters, and that is Newton seconds. Momentum is measured in Newton seconds. So here's what I'm going to do. Newtons times meters is joules. So this is joule seconds. And joule seconds are the proper way to write the units for angular momentum. And it's going to be the same if you do it for the rigid body also. Let me try that. That's going to be kg meter squared for the rigid body's moment of inertia, and omega is radians per second. Well, radians is not quite a unit, so we can get rid of it. I can do the following. I can write 1 over seconds as seconds over seconds squared. Kg meter squared per second squared, that's like kinetic energy, 1/2 mv squared. So that can be written as joules seconds. So we get the same units there as well. So I just want to show you an application of the generalized Newton second law. So here's an application. It's a problem I made up because we have to figure something out that requires this peculiar type of rule. So let me take a uniform rod and pivot it to the axle of a motor. So here I have a direct current motor that you are supposed to feed a certain amount of electricity to using these wires. I call it plus and minus. And the motor, this rod has got a sleeve on it, and the sleeve is able to move on its own using some internal threads which are themselves motorized. So it's a pretty complicated mechanism, and it's a little mini robot, for example, and it can move out with a constant speed v0. Our aim is to move this entire assembly at a constant angular speed omega naught, and we have to figure out how to feed the motor current to do so. So the problem is to find the motor torque. As a function of time. How should this torque change as a function of time? And that torque is in turn controlled by the current, which changes as a function of time based on some electronic circuits. So this is the basic problem. How do we do this? Well, the starting point is again going to be Newton's second law for rotation, the more general Newton's second law. The torque of the motor is going to be the rate of change of the angular momentum of the system. Now, the angular momentum of the system is given by the rigid body formula, so it's going to be I times omega. Now, let's suppose that this object is some distance x away from the axle at any given time, so that we can write a concrete expression for this. The moment of inertia of a uniform rod, that's given from your table of moments of inertia, it's 1/3 ml squared, where capital M is the mass of the rod. So this has got rod mass m, and let's say this has mass little m. And so for the mass of the robot, we're going to assume it's a point mass because we are told nothing about it. So that's just going to be the moment of inertia of a point mass, mx squared. Okay, because this is a point mass at some distance x away from the axle. The whole thing times omega. And we have to take the derivative of this, so let's do that. dl by dt. Well, first of all, this does not change with time, so that's just big 0. Plus the derivative of x is just x squared is 2x, so that's going to be 2mx. But x itself changes with time because the robot is moving, so that's dx by dt. And since dx by dt is given to us to be v naught, I'll write that. So it's 2mx times v naught. And oh, I forgot the omega. It's still there. Omega naught, actually. So the whole thing, omega naught. Now that's equal to the torque, so I can find the torque. But I need the torque as a function of time. Now I'm going to suppose that the motor starts out, the robot starts out at the axle at time 0. So x can be found by integrating. X is just equal to v naught t plus some initial x value, and I'll take that initial x value to be 0. So for x, I'll write v naught t. So if I put that in there, I'm going to get 2m v naught squared omega naught t. So that is the torque as a function of time, and that's how you need to feed the electric motor.